Steinhaus-style methods variant.
Thank you again, and thank you for coming for the fourth time. So what I'm going to present today will be slightly different from the first three lectures. It will not have anything to do with orthonormal basis or exponentials, but it will have a lot to do with time. So what is the Steinhaus-style algebra? So originally the question by Steinhaus was posed like this. Can we find two subsets of the plane such that no matter how I move, by this I mean translation and rotation, no matter how I move the set A, it always intersects the set B at one point. No matter, so I hold B fixed and I move A around. No matter how I do it, there's exactly one point in common. So soon after that, Sierpinski answered yes, there are two subsets. He constructed them. Now, these guys did not much care about measurability at that point in time. So sets for them could be anything. So they would use transfinite induction, invoke the axiom of choice several times, and so on. So usually what they produced was not measurable, or at least not known to be measurable. So let's state this in an equivalent way. So let the variable b run through the b points, and rho a is a rotation, not translation, just a rotation of a. So rho is any rotation. So I want for all rotations and for all x, so this is a rotation and this is a translation. For all rotations of a and for all translates of b, I want this sum to be exactly 1, which means there's exactly one b. I would make this 1, which is exactly what we want. That's two sets intersecting points. Now, written like this, we recognize this as a tiling problem. So rho A is the tile, B is the set of translates. So we want rho A to tile with B no matter what rho is. So you have a fixed set of translates. This is the set B. And you have your set A. And if you take A and you place it here, it will tile. But also, if you take A, turn it arbitrarily, and then you place it here, it will still tile. Okay? That's exactly what I just said. So the set rho A translated at B gives you a tiling of the plane at level 1. This shorthand notation, this is a so-called direct sum, so everything is represented exactly once as a sum from here and there, and that's going to be our square. Okay. So in some sense, the most interesting case, at least for the first half of the lecture, will be if we fix B to be the set of integers. So this set will be the set of integer points in the plane. This will be B. So what would we want if we fix B? We want to have a set A, all of whose rotates tile with z squared. So it's easy to find one set which tiles with z squared. Take, for instance, the unit square. If you place it at all these locations, it will easily tile the plane. But that's not all we want. We want a set such that if you turn it by any angle and you place it at the same point, it will still tile the plane. So in some sense, you want to find a single set that will imitate all those rotated squares. It should behave, as far as this square is concerned, like any one of those. Somehow play the role of all the squares simultaneously. Another equivalent way of stating this is that since rho z square is a group, okay?
Sorry, just
what we're seeking is a set A, which is a fundamental domain of this group in the plane. What's a fundamental domain? A fundamental domain of a group H inside a group G is exactly a selection of one point from every coset of H. So we all know that G can be partitioned as a, so everything is abelian here, so I'll write some x plus h, where x belongs to some set. Any selection of one point from each coset is called a fundamental domain, and it is exactly what it means to tile by h. So if you take f to be a fundamental domain of h in G, then what this means is exactly that f direct sum with a subgroup H is a tiling G. Okay? So what we're seeking here is a common fundamental domain of all these groups. We have all rotates of Z square, each of them is a group. And you want to find a common fundamental domain for each of them. You want to select one point from each coset simultaneously for all of them. So it seems like an impossible task, and in some sense we still don't know if it's possible, but you will see what is possible. Now, as far as the non-measurable study of this problem is concerned, the real major result is one by Jackson and Malden of 2002, who answered yes, there is such a set A, which tiles with all rotates of the square. It's not measurable, or at least we don't know if it's measurable. And this happens only in the plane, so we don't know what happens in higher dimensions. The same problem can easily be stated in R3. What do you want in R3? You want a set such that all rigid motions of the set will tile with Z cubed, right? So we don't know if you allow non-measurability if it exists in R3 or not. But the real question that we like to study here is whether we can do all this with a measurable set. And when you do it with a measurable set, you just interpret tiling almost everywhere. You don't mind if a set of measure 0 is covered 10 times or 0 times, as we usually do. Now, what's known here? Most of the results in the dimension T, I guess all of the results in dimension 2, are negative. So all of the results are of the following type. If such a set exists, we still don't know if it does, then it must have this and this strange proof. And okay, here are some results which I'm not going to mention very specifically, except for the one of Beck, which is the same as mine here, but probably slightly different method. Before going to my result with Tom Wolf, let me prove to you, or maybe I'll do this later, I think it comes later. The best result so far is this. What does this say? If you have a Steinhaus set in the plane, and it must be very large at infinity, certainly cannot be bounded, but not only that, its decay, the decay of its area at infinity must be very slow. This is exactly what this says. So if you integrate over A, this moment, this power of x, this is going to be infinite. Okay? The smaller exponent you manage to put here, the better result you get. Okay? And this is a very complicated result. I'm not going to say almost anything about this. It depends on the best known estimates from the circle problem. The circle problem is how many integer points are there in a disk of radius r, and you want to know what the error term is. And in higher dimension, the Lebesgue measurable case is settled by both myself and Wolf and myself and Papadimitriakis. I will give you the second proof. No measurable Steinhaus sets exist in dimension 3 or higher. And we'll see the proof of that. The second proof is really easy, and we'll see it. Okay, so let's study what does it mean to be a Steinhaus set in Fourier space. So again, we're going to look at the periodization of the function f. So you take any function f and you want to examine if it tiles z square, with z square. Then you're looking at this sum, right? You would like this sum to be 1 or a constant. So this sum is exactly what we call the periodization of function f with respect to the group z squared. We also saw it on the lecture of Friday. And this periodization has the property, I'm just repeating what I had said back then, that the Fourier coefficients of capital F. So capital F is a function defined on the torus, so it has only Fourier coefficients, no Fourier transform. But the Fourier coefficients of F are exactly the same as the values of the Fourier transform of F at the integer values. This is just Fubini, nothing but Fubini, very easy result. So if you want capital F to be a constant function, say 1, then what you want is that the Fourier coefficients are all 0 except for the constant Fourier coefficient corresponding to n equals 0. So for all non-zero n, F, this guy must be 0. Which is, because of this, it's equivalent, if you look now at the Fourier transform of your original function f, it's equivalent, the Fourier transform of little f vanishes at all these points. So for a function f to tile with this square, its Fourier transform must vanish at all these points except at the origin. The origin is always the same. Okay? But this, if you have a Steinhaus set and you look at its indicator function, it must have this property for all the rotates of itself. So if you have a function that vanishes at those points, its Fourier transform vanishes at those points, and you rotate the function, the Fourier transform also rotates, which means that the Fourier transform of f will also vanish at every rotation of this lattice. So what happens if you take the lattice z squared and you give it a complete turn around the origin? Each point is going to go through, going to cover a circle. Now these circles are precisely the circles whose radius r is the square root of the sum of two integer squares. Not every integer is the sum of two integer squares, but many are. So, more or less, if you go to distance capital R out here, the number of circles you're going to see, well, it's not exactly r squared, it's r squared divided by some logarithmic term, but more or less we just think of it as being r squared. So if the number is r squared, then what's the gap? The gap is going to be roughly 1 over square root of r. Okay, so you have those circles that are moving at not a very regular way, but more or less by gap 1 over root of r. And up to distance r, you have almost r squared of them. Now, since you have many zeros for f hat, what are those many zeros? All those circles centered at the origin that go through an arbitrary lattice point. My f hat vanishes at all those zeros. The vanishing, since f hat has bounded derivatives. Why? Because to bound the derivatives of f hat, you just multiply f by x and you integrate. A is, if you assume a is bounded, say, then everything is bounded. In any case, many zeros towards infinity imply decay of f hat towards infinity. That's natural. Of course, you have to work for it, but that's what it does. Decay of f hat implies, first of all, regularity for 1a, for the indicator function, and also implies a certain lack of concentration. It cannot be concentrated at one point. So the result of myself and Wolf comes from, as I said, from estimates for the circle problem, which in dimension 3 is much better than it is in dimension 2, but I'll now make an interruption and prove to you a simple result, one of the first results in this problem. So if A is a Steinhaus set, in any dimension actually, but I will do it in the plane, then A cannot be bounded. This is a really simple result, which is worth seeing in detail. So how do we prove this? So here is the Fourier plane. Here are the zeros of 1a hat. And let me go up to distance r. Okay. Now let me read the function, this function here, only on the x-axis. Let me just view it as a one-dimensional function. It still has all those zeros. So this function, restricted on the real line, has about r squared zeros in this interval, let's say minus r. But what is this function? The function 1a hat restricted on a line. Well, it's very simple to see that it's actually a Fourier transform of something. What is this something? It is the projection of 1a onto this line. So if my original set were like this, if this were the set A, then the way to find its Fourier transform on the line is the same as projecting the set on the line and then take the one-dimensional Fourier transform of the projection. So this set will give you, if you project it on the line, it's going to give you a function that looks like this. Function on the line. If you take the Fourier transform of that function, you read exactly, that's Fubini's theorem, the restriction of the Fourier transform on the line. So here you have a function. Now if A were bounded, this function would have compact support. What do we know about the Fourier transform of a function of compact support? It's analytic. Not only that, but we know stuff about its growth on the complex. And an easy, so if I have a length L here in the support, then it turns out that f hat, so let f be, let f be this one. Alright? So f hat in the complex plane is gonna grow not much faster than about this. I think we put the imagine up and just put the modules. Doesn't grow more than L exponential. This is immediately estimated if you just write the integral that defines this and apply a triangle. And then we use Jensen's formula. Jensen's formula counts zeros of a function. So if you are in the complex plane and you take a circle like this, and you know how large your function is on the circle, an analytic function. On the circle, then you have an upper bound on the number of roots your analytic function has in here. And if you start with such a function, then the bound you get will be linear in R. Such a function should have at most a constant times L times R. That's what Jensen's formula says if you write it down. So, contradiction. Why? Because this f hat has about r squared, when it should have the linear numbers. So it cannot be bounded. No, it's arguments like this, but much more sophisticated, that gave all the following results. So Beck proved this first, and then sort of at the same time, not at the same time, with roughly the same proof, slightly better result, I proved it too. And then I got a better estimate, and with Wolf who proved this. I had a better, worse exponent before that.
And that's the best.
That's the best so far, since 1999. Okay, as I said, we still don't know if a measurable Steinhaus set exists in the plane. Well, let's continue. With higher dimension. Why are there no Steinhaus sets in dimension 3 and higher? So let me start with dimension 4. Why do I start with dimension 4? Because every integer is a sum of 4 squares. That's the Legendre. And the trick is this. Okay, let me now erase this. Suppose in the set of zeros, this set, we managed to find a whole lattice sitting in there. So we have a definite set of zeros for a Fourier transform of Steinhaus set, and suppose I managed to find a whole lattice sitting in here. I'm clever enough to find a whole lattice sitting in here. Let's call that lattice lambda star. Star is a dual lattice. You will see why I do that. If I find such a lattice, then I know that my somehow set, let's call it T, tiles with lambda, not lambda star. Why? Because what does it need to do to tile with this? You need the Fourier transform of lambda, which by the Poisson summation formula is lambda star, to be the 0. So that's exactly what we get. So if I find a large lattice or any lattice in there, I get a tiling. And the crucial thing here is that this tiling, the level of the tiling, must be an integer. Why? Because I'm moving around a 0, 1 function and I add it up. You can only get integers like this. So I'm looking for lattices in that set. So here's the Lagrange theorem. All spheres of radius root n are in the 0 set. This is exactly what I said before. Every integer n can be written as a sum of 4 squares. So the number of spheres where the vanishing happens is known exactly. So you go to distance r, you have r squared spheres. And let me now look at this quadratic form. So I define this matrix. It's a 4 by 4 matrix. It's not hard to see that it's positive definite, which means that this is always non-negative. And it's also very easy to see that it's integer valued. If you multiply, if you look at this, what it is, then you're going to have the summation of xi squared, and you're going to have 1/2 xi xj, but you will have it twice. So if you plug in integer vectors, you get an integer back. Okay, so that's a quadratic form which is integer valued. Since it's positive definite, you can find the square root of this matrix. Let's call it root b. And let me define the lattice lambda star to be the square root of b times z4. Now this implies exactly that all these points, their square of their distance from the origin is going to be an integer. Why? Because their distance from the origin is root bx. Take this digits of adjoint, so you put them here. You get exactly bxx, which are integers. So all the lambda star points for this lattice lambda will be on those nice circles where I have the vanishing. So I have tiling. So what kind of tiling do I have? How do I find the level of the tiling? The level of the tiling is always the volume of the set times the density of the lattice. Always. What is the volume of the set? 1. What is the density of the lattice? The density of the lattice is what we call the volume of the lattice, or the determinant of the matrix. You calculate it, it turns out to be root 5 over 4. Not an integer. So we have found a counterintuitive. If we could find a set, this would lead to a tiling level which is an integer, but that would mean that this should be an integer tiling, which is not. Because root 5 over 4 is not an integer. So this disproves the existence of measurable Steinhaus sets in dimension 4. How about dimension 3? This guy here is Legendre, who proved the following, that, okay, in dimension 2, the problem of representation of an integer with the sum of two squares is a really hard problem. People are still working on getting estimates and better estimates and so on. In dimension 3, it's not as nice as in dimension 4, where everything is represented, but almost everything, we know exactly what happens. Any number is represented as a sum of 3 squares, except for the number squared of the 4 to the nu times something which is 7 mod 8. This is not exactly, this is Legendre's theorem. Okay, so we found, myself and Baba Dimitrakis, we found this very nice quadratic form in 3 variables, and we proved that the values for x, y, z being an integer is always a sum of 3 squares. How we found it? Well, I experimented with the computer quite a bit, using some shortcuts that I knew had to be satisfied, and found this quadratic form. We satisfied this up to several million, and I said to my colleague, okay, I did part of the work, now you do the rest, prove it. And he proved it by the next day, and that's it. But 2 times 11 times 6 is not a square. Which means what? That if I take this lattice, which is exactly what will give you square norm this, if I take this lattice, It is contained in the spheres of vanishing in dimension 3, and it does not have an integer volume. Again, okay? The square root of 211.6 is not an integer. You have only 1 3 there, only 1 11. Okay. So that takes care of dimension 3. Okay? There's a story here which I think is nice. For a long time, people thought that this was Legendre. You can find several books where this is like. At some point, Peter Duren, a very famous complex analyst, I don't know why he cared about this thing, but he dug up and he realized that that's not Legendre, that's some other guy. I don't know who it is. This is Legendre. And this is Fourier. You observe how much happier Fourier is. And if you look at the historical record, Legendre was indeed a very rough guy, and it was not easy to deal with it. And so this is Legendre. This guy is really happy. Okay. Now we leave the original Steinhaus problem, and we start looking at its variants. The first variant that makes sense to look at is to moderate your expectations, and instead of looking for a set of tiles with all rotates of z squared, why not look for a set that tiles with 10 rotates or 100 rotates of the square? And why restrict yourself to the square and not to the general lattice? There's no real reason. So suppose we start with n lattices in Euclidean space. Now, if I want to find a common measurable tile for all of them, they better have the same volume. Because something that tiles with lambda 1 must have area or volume equal to the determinant of lambda 1. So they must all have the same determinant. Can we find a measurable A which tiles with all of them? All n of them? The surprising answer is yes, most of the time. And for 2 lattices, it's always that. I mean, it was surprising to me. And it goes like this. We use somehow the fact, okay, the real assumption here is that we demand that the sum of the dual lattices given is a direct sum. What's a direct sum? I do not want any selection of a point from here, plus a point from here, plus a point from there to add up to 0. No relations, in other words. So if this is clearly the generic case. If you select them at random, they will satisfy this. Now, if you have such a direct sum, then it's an analogous phenomenon to what we have in one vertex. The multiples of an irrational number are dense modulo 1, right? If you look at the multiple integers, they're dense in 0, 1. The same thing happens here. That if you take any 2 of them, say, then you can translate mod 1 to whatever you want modulo the other, more or less. So, how do we construct this common tile? We'll give you the construction for two lattices. So suppose I'm given 2 lattices in the plane, say, lambda 1 and lambda 2, which satisfy this assumption. This is a direct assumption, no relation. So as I said, this implies a Kronecker theorem, that I can take any point, if I start from any 2 points on the plane, I can move this by a lambda 1 and move this by a lambda 2 and bring them as close to each other as I want. This is how we use it. Okay, now how do we use it? We start, let's say this guy is z squared. Okay, and let's say this guy is some rotate of z squared, just to make a good picture. So I start with a square here, which is the tile for lambda 1, and I also start with a rotated square, which is a tile for lambda 2. So I have these 2 tiles, one for the other lattice, and one for the first. Okay? So I would like them to be the same object. They're not, but part of them is. So let me just right away keep this common part of these 2 squares. I declare this to be part of my eventual set. This I keep. It's common to both of them, to both fundamental domains, but then I have leftovers. So for instance, I have this part from the first square and this part from the second square. what do I do? First of all, let me draw a better picture. So these are the two of the leftovers. I drew a grid, relatively fine grid over them, but I more or less split them all to little squares, let's say epsilon by epsilon. And then I take one square from one square from the other, say this square and that square, and I translate the first one. This is for the lattice lambda 2. So I translate it here, and this guy from lattice lambda 1, I translate it very close to that point. What do I get in the end? I get this picture from this guy, and this picture, say, something like that, from the other guy. Now, translating part of the fundamental domain with some lambda 1 does not change the nature of the thing. It remains a fundamental domain. Nothing changes. So now, I just managed to have them, to make them have a very big common part. So now I'll keep this. This will be part of my domain. And I have new leftovers, but the leftovers always get less and less and less in area. So you do this procedure forever. You pair your squares one with each other. You have a second generation of leftovers. You draw another finer grid. You pair the new squares and so on. In the end, you have measure 0 left. And that's it. And what comes out is a set which it's actually a set of polygons, but they extend all the way to infinity, because to apply Kronecker, you need to go far away. It's still an open problem. If you can find a common tile, say for these two, which is bounded. We don't know. So this variation, in most of the cases, is an affirmative solution. You can always find a common tile. Now, I'll state the same problem in a more algebraic language, because this is really what's behind this question. So we have an abelian group, and we have also some subgroups of the same index. The index is how many cosets each of them has. Let's assume everything is finite, just to be on the safe. Can we find a common set of coset representatives for the Hj? So G is partitioned by Hj in cosets, by H1 in cosets, by H2 in cosets. Can we select a common set of representatives from each? This is the problem. And it's always possible for two subgroups, even in the non-abelian case. This is a standard textbook exercise, actually. But it fails in general. For instance, there's this very simple group called the Klein 4 group, which has 3 copies of Z2 in it. So you can imagine this group. There's one copy of Z2, another copy of Z2, and another copy of Z2. They cannot all have the same fundamental domain. It's very easy to check by inspection. So it's not always possible for 3 subgroups. But we still lack any real condition on when this happens or not. Not even necessary solution, even natural one-directional conditions. So no, don't know any good conditions. If anybody likes algebra a little, this is a nice, but probably not very easy problem to try. Now let me give you an application just to see that these questions are not only for us to write papers and get grants and travel to places. Sometimes other people use them to prove more applied stuff, although one can always debate what's applied and what's not. So there's in applied harmonic analysis, one often looks for a so-called Gabor orthogonal basis of a space, or Weil-Heisenberg orthogonal basis of, let's say, Euclidean space. And what are these? You have some set of translates and some set of frequencies and a fixed window function, function g, we'll call it a window function, such that when we take all translates of g with all possible modulations, as we call it, then you get an orthogonal basis. For instance, if you take g to be the indicator function of a unit square, and you take the set k to be the integers and the set L to be again the integers, then it's very easy to see that this is indeed an orthogonal basis, because all the translates will tile my space nicely, and on each translate, these guys are an orthonormal basis. So that's a simple number of reasons, but there are others. And the question here was, I mean, there's this condition, volume of K times volume of L equal to 1. This is easily seen to be a necessary condition for this to be an orthogonal basis. There was an outstanding question: what if we have two lattices which satisfy this assumption? Can we always find a window, G? That will give us a couple of bases. That was open. And after I proved my theorem, Han and Wang actually specialized on the case of 2, n equals 2, and they proved that for the case n equals 2, no condition is necessary. It's always possible to find a common fundamental domain. And then if you take E to be that common fundamental domain of K and L star, which must have the same volume because of the condition, then the indicator function of that fundamental domain is easily seen to form an orthogonal basis for the whole space. Because the L frequencies will form an orthogonal basis for E. Why? Because E tiles with L star. And then the whole space is partitioned in copies of E. Why? Because E is the fundamental domain of K. So on each copy, you have the frequencies required to do your harmonic analysis. So the entire thing is an informal basis. This uses the result of about 2. Okay. Now I have 2 more problems to talk about. Now, it's a Steinhaus set in slightly more, so go back to the generality, keep measurability. So the original question was, there an A such that all the rotates of A tile with B? And then we specialized with B to be the integers, and we did all sorts of work. But now let's change B. If I take this B, the blue points, which is the integers in the plane, and I take this strip here of width 1, this strip tiles with B. If you translate it on integers, you will fill the plane exactly. And you can also look at a finite set B. For instance, these 3 dots. If you have this finite set and you take this gray set, it also tiles with this finite set, just 3 copies of that. Now, in both cases, the tile will be of infinite measure, but we don't care. So it's exactly these 2 cases that I care about. Can I find a Steinhaus set for this B and for this B? And what's known? It was proved by Komiev that there is such a set, that for the integers, if I take B to be the integers, so the first set here, then Komiev proved that there is a set A which tiles with all the rotates of this set. So if you move it like this, it tiles. If you move it like that, it tiles. In all directions. But it's not measured. And this is provable. I will prove to you it's not. And for the case of a finite set, there was lots of papers who were dealing with finite sets of specific, too many cases, not very interesting in my opinion, but they did this by proving that there's no such set, measurable or not. Okay? So I will prove to you that no Komiev set can be measurable, and there's no measurable set that does this for any finite B. These are the proofs. And let me start from the case of finite B. So let B be a finite set in the plane. I encode B with this measure, I put a Dirac mass at each point. Then its Fourier transform will be a trigonometric polynomial with coefficients 1 and frequencies at B. Okay. What does it mean that A tiles with B? It means that this convolution is a constant. Okay? Exactly this. If we take the Fourier transform, of course, we read this. We did this last time as well. And we want the support of 1A hat to be in the zeros of this trigonometric polynomial. Now, 1A hat is not necessarily a function, it's a temporal distribution. Why? Because A doesn't have finite measure. So you have a function which is not in L1, it's bounded but not in L1. You take its Fourier transform, you don't get a function back. You may get a measure, or you may get a temporal distribution. And you want this to be true for all rotations of A. So if this is valid for all rotations of A, my zero set must contain all rotates of this support. So my zero set must contain at least one circle. I have a trigonometric polynomial, this one, whose zero set contains at least one circle. This is not possible. This is another surprising result. I think this is a simple question that no one had looked at before. The proof is not hard, but it's kind of unexpected. You have trigonometric polynomial. Why? I still really don't know why this happens, but it cannot contain any circles or spheres in its Fourier zeros. So this is the theorem. Take any trigonometric polynomial in any dimension, and if it vanishes on a sphere anywhere, then it must be zero. Let's see how it goes. This is also, by the way, common work with proper limit right. So here are my frequencies of the trigonometric polynomial. If I translate the b's, the zero set doesn't change because the Fourier transform only gets multiplied by an exponential, so the zero set don't change. So I can translate my b's to achieve the following, that I have a unique point of the b's with maximum modulus. So this is the most distant from the origin, and there is no other with equal distance. You can always achieve that by pushing things far away. Okay? B0 is the farthest point. Now, let me write in code. Now I work in complex variables. I will work in two variables, and then the d-dimensional result will follow very easily. Because if you contain a sphere, then your projection, which is still a trigonometric polynomial, will contain a circle. Okay. So we'll work now in two dimensions. Let me encode the b's with complex numbers, exactly like that. And x minus iy, I call it z. And then the inner product of these two real vectors is exactly the real part of the complex multiplication of b times z. So I can rewrite my trigonometric polynomial like this. And suppose the circle where it vanishes, I can always inflate things like that and make it to be the unit circle. So at z equals 1, this should be 0. So what happens at z equals 1? The real part of bz will be bz plus its conjugate over 2. So it killed that 2. But the conjugate of bz is b conjugate, z conjugate, but z conjugate is 1 over z on the unit circle. Z conjugate is 1 over z. And let me call this function g of z, which is 0 on the unit circle. If it's 0 in the unit circle, it's 0 everywhere on the complex plane where it is defined. It's not defined at 0, but everywhere else on the complex plane, this function is defined. And if it is 0 on the unit circle, it's 0 everywhere. By analytic continuation. Now, move towards minus infinity, going downwards in the y-axis, minus it. So let t go to plus infinity. And separate the largest term of your trigonometric polynomial, b0. This will become b0 times t plus something that goes to 0. So as far as growth is concerned, this will play no role. This determines the growth. And for the other guys, you do the same. So this determines the growth. But all the b's that are here are strictly less than b0. So you have a sum, which is 0 of exponentials, with a unique leader. The others cannot catch up. These are exponentials. This cannot happen. So this is impossible. So since we cannot have a circle in our zeros, all the sets that tile with b and all its rotates must be non-measured. I'm sorry, must be non-measured. So we dealt with the finite case. The other case is actually more interesting. So Komiath proved that there are sets which tile with this set of translation. And I will prove to you that no such set can be measurable. So what does it mean to tile with this set of translates? This is the set of translates. It means that this sum is 1 for all rotations per row. Okay? Now this immediately implies that A has infinite measure, just to keep this in mind. But the important thing here is this. That if you integrate this from x goes from 0 to 1, it's as if you're going to be counting the measure of row A along this line. And since for each x you read 1, you will get measure 1. So what did we prove here? That rho A has measure 1, one-dimensional measure. Okay? Measure 1 on actually on every horizontal line. Because nothing is special about y equals 0. Whatever happens here happens there, and so on. And since you have an arbitrary row here, so you don't have only those lines, you're going to have also those lines, every line. So what we have is that A has measure 1 on every line in the plane. If a measurable Konya set exists, then it must have measure 1 on every line in the plane. Now this sounds very strange, but stranger things can happen in mathematics. So you have a set A spread out over the plane that has a measure, and no matter which line you look, and you integrate your set A, you see how much length you have on this, you have 1. This, I will show you, is not possible, but it's not immediately. In fact, the proof we have, I still expect that somebody will find a more clever proof than this, or more direct, I should say, because this is quite clever. And I'm saying this because I was not the one who found it, Papa Dimitriakis found it. So, this is the theorem. If we have any measurable set A in the plane, which intersects almost all lines, we don't have to do it for all lines, at a length which is between two positive constants, it doesn't have to be exactly 1, let's say between 1 and 2, no matter which line you look at, the length is between 1 and 2, this is not possible, okay? And we get the Komiath result by choosing C1 and C2 equal to 1, but it's more general than that. Okay, suppose we have such a set, which has this bounded line intersection property. Now we view this set as embedded in R3. So here is R2, and we put an extra dimension. And we define a function in R3, call it f, by this formula, where z minus w is the distance of z and w, the Euclidean distance. Now this clearly defines a function everywhere, and even on the plane, because the function 1 over r is integrable on the plane. Okay? And the function 1a is bounded. So this is defined everywhere. And what I'm going to show now is that this function is bounded everywhere below and above. Bounded to begin with on the plane. And then I'll show it's bounded everywhere, but to begin with, I'll show it's bounded on the plane. And for this, I will use the bounded line intersection property. So I start with my function, which is given by this. Now let me change my variable. Z minus w will be my new variable. So it becomes now like that. Just simply change the variable, and I write this in polar coordinates. So 1 over w will go away, and I have 1a at z plus r cosine theta sine theta. R, I let r take negative values, and I let my angle only go up to p. Now, what do I read if I do the inside integration? Theta is fixed, it's a fixed vector which I multiply by r, so I'm running along the line. So I'm integrating essentially the measure. The inner integral will give me the measure of a on this line, z plus L theta, where theta means direction theta. This is what I'm integrating. But this quantity, by assumption, is between C1 and C2, because A has a bounded line intersection property. Therefore, this quantity will be in this integral. So I got this on the plane, but f is defined everywhere. I'm not going to prove that f is continuous. It's not surprising. It's just elementary, but you need to cut and do things like that. I don't think there's anything here. And we have, as I said, we just proved that it's bounded on the plane. What happens in the other dimension? Now we notice that f is harmonic. It's a harmonic function because it's a weighted integral of harmonic functions. 1 over r is harmonic in R3. So, at least in the upper half space, we have a harmonic function f which is bounded on the plane. It's also continuous. Now, for a point z in space, let z prime be its projection onto the plane. Because of the way we defined our function, which is the integral of 1a this is W. If you go from z, W is in the plane. Right, so this measures the distance. So here is z. This is the plane where A sits, and this is the point W in A. This is this distance. If you project it down, z prime, this distance gets smaller. So the function gets larger. Okay? So f of z prime is larger than f of z, but f of z prime is on the plane. So by the previous result, it's bounded by c2 times p. So what I will have a function f of z, which is harmonic in the upper half plane, bounded from 0 to pi. And there's a nice theorem in harmonic analysis that if you have a harmonic function in the upper half plane, bounded everywhere, and continues in the closed half space, then this function arises as the Poisson mean of its trace on the plane. But a Poisson mean is a mean. If my function f of z on the plane satisfies this, then it satisfies that everywhere because it's an average. It's a mean. Okay, so we get this thing. But this is a contradiction. Why? Because if you go, if you keep x and y in the plane fixed and you go up to plus infinity, it's very easy to see. This quantity goes to plus infinity. You're going very far away. This whole thing goes to 0. But I have a lower bound. F of z is bounded below by a positive constant. It cannot go to 0. Contradiction. Therefore, it's not possible. And I think I'll stop here.
Thank you very much. Any question or comment?
And I strongly expect that somebody will at some point find a simpler proof of this fact, at least for the case when you demand that a set touches every line at length precisely 1. Maybe if you allow two constants, the harmonic functions are necessary, but if you insist on measure 1 intersection with every line, I expect there must be some more clever way to do it, but I don't know.
So if you know some flippings, this can reduce to rotations, but not to all rotations, but to some.
If you allow flippings for your set, or what do you mean exactly? So,
yeah, if you allow some, let's say, triangle, you allow.
the triangle cannot tile by translation, but it can tile if you allow flip. And so you mean to ask the same question by not translating, let's say, z squared, but translating with a given set of rigid motions, essentially.
Which can be realized in a plane, let's say, by rotations,
Yeah.
but you mentioned there are some kind of, you can rotate by multiples of 90 degrees, for example.
Yeah. Say reflection and translations.
Does it reduce to the, because you can also take finite Riemannian.
No, reflection does not reduce to rotation, that's for sure.
But you can find, in any of these questions, you can find, let's say, you can put finite Riemannian on them, and then this is new set, and then you try to trial, but you don't know where the set is exactly. So,
But you don't know a priori. So where you're going to have the triangle and where you have the flip triangle.
exactly.
So it's not clear what the question is.
So it's not doesn't reduce, but is it? But still, you can have Fourier analysis once you, let's say, flip it, and you can Fourier analysis is related.
Fourier analysis will have to be done on a higher group, not the plane. Because, I mean, in essence, you have the group where you have the plane, which accounts for translation, and some kind of semi-direct product, perhaps with Z2, which accounts for flipping. That's where you have to work. Because you don't know a priori where you have your flipped triangle and where you have your unflipped triangle.
So I was just curious if it makes sense, this kind of question.
Certainly makes sense. I cannot do it, but certainly makes sense.
Okay, any other question? Okay.
Ja,